So in this last section of lesson 6.3, we're going to focus on application using word problems to understand how exponential functions come up in the real world, what kinds of situations might have these kinds of patterns. And we're also going to review something we've done before with linears, but we're going to do it with exponentials now, which is a regression. When we gather our own data, and then we want to see if we can find a good curve of best fit. We did this with linears when we would gather our own data, and we thought maybe that data might have a linear pattern or could be modeled by a linear equation accurately. We would do a linear regression. Well, we're going to do the same thing, but we're going to do exponential regressions. If we make a scatter plot of data points or data that we've collected, and we notice, hey, that doesn't really look like a straight line, but it kind of has that curve shape that might be more more accurately expressed as an exponential model, then we could run an exponential regression and have the calculator give us the curve of best fit and what the exponential equation would be that would best fit the data. And so a lot of those steps are going to be identical to what we did with linears, except we're going to select exponential regression instead of linear regression. So we'll review that, okay? So, but first of all, let's just look at, we've talked about the characteristics for exponential functions, being able to identify them, evaluate them, graph them accurately. So now we're going to see it in application. And let's start with this first example. It says the graph represents bacterial population, which is represented by Y. That's our population after X days. The first thing we want to do is write an exponential function that represents the population, and we want to be able to identify what that might mean. So we've got some data points in our graph that are going to help us do this. It looks to us like we have an ordered pair at 0, 3, and then at 115, and so on. And what I'm going to do is I'm going to take the same ordered pairs that they're giving us there and just reorganize them on a table so we can see patterns and y-intercepts and such maybe a little bit more easily. So that's the first thing I will do, is just kind of transfer that data into a table. So the first ordered pair I see here is when x is 0, y is 3, and then when x is 1, y is 15, or f of x, same thing. When x is 2, we've got an output of 75. At 3, it is 375. And then at 4, it is 1,875. So there's our table with the 5 ordered pairs they gave us. And that, I think, is going to help us answer the first part of this. So when it says write an exponential function, we want something that looks like this, and what we want to be able to identify is what is that A, initial quantity or y-intercept, and then what is B, the kind of rate of growth. What are we multiplying by, essentially? So if we look here, I can see that when x is 0, this is all just going to, when x is 0, this whole term would go away and I would just have A. So I know that y equals A is always where my y-intercept lives. So looks like my y-intercept is at 3. And then I can tell here that repetitively we're multiplying by 5. And how I can easily tell that is if I take the new divided by previous. If I do y2 divided by y1, 15 divided by 3 is 5. 75 divided by 15 is 5. 375 divided by 75 is 5. Every time I divide the new by previous, I get 5. So that is my multiplier, or the base of my exponential function. Okay, so if this would be my, and I guess I should be using an f of x here, so let's do that. So there is the exponential function where a is equal to 3 and b is equal to 5 here. And what that means is that our y-intercept is 3. So what might that mean is at 0, 3. If we were going to interpret, right, because it says identified, well, we just did that. And if we're going to interpret what that actually means, it means that on day 0, at the beginning of this particular experiment, they must have started with just a population of 3 bacteria cells. Okay, so I might the experiment began with 3 bacteria cells. Okay, something like that. And then it's increasing at this rate every day. All right, so we wrote an exponential function that modeled it. We identified the y-intercept, and we interpreted what it meant. Looks good. Then it says in B, describe the domain and range. We haven't done that in a while, so let's review that. Domain is a set of input values, a set of possible x values that could be used here. And I can see here it doesn't really make sense to have negatives because time won't be negative. We either just started the experiment and then we moved forward in time. But time is something that is continuous, it is fluid, it gradually increases from one to the other. So because it's continuous, I'm going to express it as an inequality and say that the domain here is the x values that are greater than or equal to 0. Okay, so we started the experiment at 0, and when that sort of experimental timer started, it just continues to go on and on. And we could run this for maybe 1.5 days or 1 day and 11 hours, that kind of thing. So it makes sense that it would be more of an inequality. And then let's talk about the range. The range is the set of possible outputs, right? And so the set of possible outputs here is just what kind of population values make sense or are valid here. Well, we started at 3. So we're starting at 3, and from there we move forward. However, these are bacteria cells. These are things that just, you get 1 cell, then 2 cells, then 3 cells. It is not something that, we're literally counting the bacteria cells. We're not measuring them necessarily. It's a population count. So I am going to say whole numbers that are greater than or equal to 3. So we could say whole numbers greater than or equal to 3. And it's a pretty simple. We could even do this in set builder notation if we want it to be super amazing and say all the y values in the whole number set such that y is greater than or equal to 3. That would be so cool. And that's a good review right there. Okay. All right. Let's take a look at part C. That was our domain and range. And then it says find the population after 5 days. This is where having a function already established really helps. Because once you have your function, then you can plug in and find any other value. So for this part here, if they want us to find the population after 5 days, then all I'm going to do is evaluate my function for when is x, right, the number of days, 5. So f of 5. And in this case, that means we're going to do 3 times 5 raised to the 5th power. And we'll find out what that is. We can grab our calculator because that's going to be a big number. So you can see these exponentials really grow very quickly. So I can just evaluate that here. And yep, sure enough, very quickly. So at 5, and I can fill that in my table here, we expect to have 9,375 bacteria. Okay. Let's answer that here. 9,375 bacteria cells. Okay, so there'll be that many cells after 5 days. So that just gives you an example. There's a lot of things that grow exponentially, and bacteria, that cancer cells, bacteria cells, that kind of thing can be one of them. Let's consider this one right here. This next example just shows a graph, not so much in context, but we will still want to be able to identify some of these key features. So write an exponential function that represents the graph. Identify what the y-intercept is. So once again, we want to write an exponential function. We need to be able to identify what is our a value and what is our b value. A is going to be where we began. B is what we're multiplying by every time. So let's take a look. If I can find here, there's my y-intercept. I know that's my a value. So I can see here that this is all going to start off with a y-intercept at -1/2. Okay. So that's our a. And then I need to know what are we multiplying by every time. So again, you're going to take y2 y2 divided by y1, always new divided by previous if you want to be able to acquire the right value there. The other thing you want to be careful here is some of these are at x values of 0.5, so that's not a whole difference. So let's not pick those. Let's pick these two, the one at -1 and 0. So that went from, if I divide those back, it would be -1/2 divided by -2. And if I do that, all right, there it is. So just make sure you're picking points that are going up in increments of 1 on the x-axis. So I'm going to go for this one and this one, because I can compare this change in my y, that ratio, over 1 unit in x. So there's my b value, and all I have to do is fill that in, and we have our function. So there's a function that models that curve. Let's describe the domain and range here. So for a domain, it is the x values. This does not have this kind of context that might limit my x's. This is just a regular graph, so I can see it goes on to the right and toward the left in both right and left directions. So as usual, unless it's a word problem, these exponential functions will have a domain that is all real numbers. And then as far as my range, looks like it's everything below the x-axis. So it goes on really quickly toward the negative, and here it's going to approach that asymptote of 0 infinitely, but never quite reach it. So it's all just y values less than 0. Okay. All right, let's flip that over and talk about reviewing regressions quickly here. So we have an example of the number of minutes that have passed since a cup of hot coffee was poured, and the temperature of the coffee as it just kind of sits there on the counter. And we're just going to go through the steps on how to do this on the calculator. I also gave you guys a sheet of paper that walks you through it, but really it's review with the exception of one kind of button press on the calculator. So we have this information. The coffee starts off at a temperature of 175 degrees, and then every minute that passes, as you could probably expect, little by little, that coffee is cooling, cooling down. So we're going to do a few things here. First of all, use a graphing calculator to find the exponential function that fits. So that's where we're going to do that exponential regression. Then we're going to plot the data and graph the function in the same viewing window. We'll do that on the calculator to just see if it's, what that looks like. And then we're going to use the model to predict what the temperature of that coffee might be 10 minutes after it's poured. So once we have a regression, that regression can help us make some predictions. Okay, so I'm going to grab my calculator here. And I cleared my RAM. So they didn't ask me so much about the correlation coefficient, but I love to get into the habit of just coming down here and turning it on. It's just nice to see it. Even if they don't ask for it, it gives me good information. So I'm going to make sure that that is on. And then I'm going to come to my stat like we did before. I'm going to edit my list, and I'm going to go ahead and enter that data into the calculator. I'm going to feed it in. So my x values look like they go from 0 to 8. So I'm just going to go 0, 2, 3. Okay, so there's my 8 minutes, my starting number, and then 8 minutes afterwards. And then let's put in those corresponding temperatures. And 75, so there it is. And then let's run our regression. So the only difference is once our data is in here and we go back into stat, and like before, we're going to want to calculate. Our data is already in there now. We don't need to edit anymore. We're going to calculate. Before, we were going right to that number 4 because we were really thinking, oh, our data is probably going to be linear in nature. Those scatter plots kind of had that straight, even if it was kind of a scattered, it was a straight line type of pattern. And so we were thinking, a linear model is going to really fit this best. But now we want to do an exponential. We're thinking, well, they're hinting to us, but we're gonna compare a little bit later. We want to go down a little bit further to right here. It's a choice 0 on this version of the calculator, but you're looking for this EXP regression for exponential regression. And then we're going to select that. Notice this looks really familiar. Everything else really is still the same. I'm going to go ahead and store it like we did before. So I'm going to go alpha trace. That's going to pull up the y equals menu for me. I'm going to say, go ahead and store that for me there in that y1. Okay. And then I can come down and actually calculate what the regression is. Okay. So here it is. There's my R value. Looks like things are looking pretty accurate and strong. It's negative. Well, that makes sense because my temperature is decreasing. So I would expect kind of a downward correlation here, and a negative correlation, but it's very strong, so it looks good. And there's my A value, which is pretty close. The predicted A initial quantity is pretty close to our original real actual starting point. And then looks like this is our B, which does look like it'll decrease because it's 0.9. So that is a decreasing. When we repetitively multiply by a decimal like this, it's actually going to decrease. So all of this is consistent with what I would expect to see. So I'm going to write this down. So the model that best models our situation here, 1.73, I'm going to round to the nearest hundredth here, times, and then 0.9 is our B. So there's our best fit model for the data that we collected on our coffee. Okay, so once we have that, that's use a graphing to find the function that takes care of A. So let's label that. Okay, B, we'll plot it in a minute. B will then be predict for 10 minutes. So when X is 10. So in fact, we could do that right now, honestly. We could just plug in a 10 and solve it, but we'll graph it first. So I'm going to come to my Y equals because I copied it over. There's my data. I'm going to move up a little bit and hit plot and actually turn it in. That way I can actually see the scatter plot graphed along with the equation. And then I'm going to press zoom 9 will graph to the scatter plot data. So there's a curve, there is our data, very good fit, right? So that's what they wanted us to see and do there. And it does look like an exponential model is the best fit here. It would probably fit better than a linear. Okay, but here's the nice thing about what we just did. Because so we got to see that, that's awesome, right? Because I went ahead and put in our model here, I can go second table and pull up a table of values, kind of like we did with our project, with our measuring our radius and our height, and compare what the model's predictions are. And then these are the actual data. So the actual data is here, that's awesome. But this is what the model would have predicted, and that's what I want to use to plug in and that 10, right? So I could work it out, or I could come here to the table and say, oh, well, according to the model, after 10 minutes, our temperature will be at about almost 61 degrees. All right, so 60.87 degrees. We'll just round out to 61. So for part B, after 10 minutes, the temp will be about 61 degrees. Okay, and then we could probably have a pretty interesting conversation of whether this is going to continue this way. You know, is it going to always be a good fit, or will eventually, be less accurate? And part of that is that this coffee is probably cooling to room temperature. So if the room is at 72 degrees and once it reaches the same ambient temperature, it's going to stop cooling, right? It's not like it's just going to keep getting colder and colder and then freeze and so forth, right? It will slow down. But right now, this is the best model for those first 10 minutes. So there it is. Okay. All right. So I want y'all to try one here. And just go through the steps on number 4. Use a graphing calculator to find the exponential function that fits it, and then predict after 5 years. So pause the video, give it a try, and then we'll reconvene here and see how it went. All right, so check to see how this one went. When I did the exponential regression, I got a y-intercept of 31.25, which is pretty accurate to that initial population, and then a rate increase of 1.6. So this is our multiplier, and that I rounded some of that. And then when it says predict the population after 5 years, we're really looking for when is f of 5, what is the value for f of 5. So we input a 5 as our exponent, and these are fish, so decimals don't really make sense, so we would round to the nearest fish. So I got approximately a prediction of 375 fish at year 5. Okay, so in 5 years, there'll be about 375 fish in the lake. Okay, all right. let's finish off with one last word problem, and then we've got a few practice problems on the other page that you guys can do and bring back to class. So for 10 years, the population of a city increases in a pattern that is approximately exponential. Using exponential regression, you fit the function right here to the population data. So they're actually have done the regression for you here, okay? Where P is a population in thousands, keep that in mind. So that really means 15,000 people of the city in the year T. So depending on how much time has passed. So what is a reasonable prediction for the population of the city after 12 years? So we just have our regression already created for us. We just want to evaluate that for what it would be after 12 years. So we would take our function and evaluate it for P of 12. So that'd be 15 times 1.064 raised to the 12th power. And then we would get an approximation for that with our calculator. Okay. And let me quit out of that. So this one, I just have the equation here. I'm going to just jump right in. So we're starting off with 15, meaning 15,000. And then our multiplier is 1.064. And we're going to raise that to the 12th power. And I get 31.57. But remember, this is really, so this right here is approximately 31.57, let's say 8. But remember, that really means in thousands. So when I interpret this answer, what that tells me is that in 12 years, a population will be about 31,578 people. So let's write that down. So in 12 years, if I write it down, you write it down. The population will be about 31,578 people. Okay. Oh, you can't see that. There it is. All right. So be careful. That's a, if they say in thousands, that you got to make sure you're like, oh, 31 people are going to live there. No, this is all in thousands. This represented really 15,000. They're getting rid of the zeros to simplify the equation, but this really represents 15,000. And then 12 years later, there'll be 31,000 people. And then it says about how many years will it take for the population to reach 50,000. Now, remember, 50,000 means we're going to be looking for a 50 in our equation. This is more interesting. Instead of them giving us a time and us just evaluating, they're giving us the output or the answer. We're looking for, it says how many years. That means we're looking for T. Will the population reach 50? They've given us the output. Okay, so we're looking for how long would it take at what exponent this would equal 50. So basically something that looks like this. We're looking for what would T be when this is equal to 50. Now this is pretty tricky right now because we haven't learned, and you won't this year, you won't until Algebra 2, learn how to kind of do the inverse operation and solve for T. And so we can't do the typical, oh, we'll just kind of get rid of everything around here and solve for T. We're not quite there yet. So what we're going to do then is just really use our table here of values and estimate. So we're going to grab our calculator. Let me turn off that plot just to be on the safe side. I'm going to clear this out. And then I'm going to enter this equation. So it's 15, 1.064 raised to the x, which is the same as T. And then I'm going to go to my table and I'm going to look for a 50 as an output. And I'm going to try to get as close to that 50 as I can. So here's my Y outputs, 48. So there I am at 48.7. This one's at 51. So it's happening, it looks like it's going to happen somewhere between 19 and 20 years. So between 19 and 20 years, maybe 19 and a half years or so, we can expect a population of about 50,000. It's going to happen somewhere in that year, that 19th year. Between the time the 19th year starts and between the time the 20th year starts. So somewhere in that 19th year, we're going to get at a population of 50. And right now, that is the best and only way that we're going to be able to achieve this goal of working backwards and finding an exponent when we have the output. Okay. So when we do that, T is going to be between 19 to 20 years, somewhere in between that. Okay. So the population will reach 50,000. when people, or 50,000 people, yeah, in 19 to 20 years approximately. Okay, and that's the only way we're really going to do that, is to just pull up a table and then just estimate it out by looking for when is the output. And notice I used 50, even though we're talking about 50,000, because our equation, our function was set up in thousands. So when we see just the numbers, we know it's really in thousands. So when I put in a 50, it really means 50,000. All right, so use a table. Let's write that down so we just remember. So use a table on your graphing calculator to estimate this answer. Okay, there's not really, I mean, there is an algebraic way, but we're not learning it in Algebra 1, so this is kind of our go-to tactic. Okay, and that is our lesson. This refreshes your memory on doing regressions, and it shows you sort of some applications in real life situations where you have exponential functions. There's problems over here. I want y'all to try quick 4 problems, give them a shot, and then we'll discuss them when you get into class tomorrow. Have an awesome day.